Hi, today I'm going to talk about Fourier series for signals and system students. So I do expect everybody who is listening to this lecture to have quite a bit of basics of signals and systems, and you can either use this as a revision, or if you're hearing this for the first time, I would recommend you going ahead and going through 3 Brew 1 Brown videos from YouTube, or Smarter Everyday video on Fourier series from YouTube, and then come back to this if you really want to. And this is just a different approach to it, but this is geared towards students who are in signals and systems. And I'll throw a little bit for people who like chocolate cake. And I'm Emmanuel Manohar. I'm from the University of Alabama. All right, so these are the basics that I expect you to understand before we get into the subject. So first, you need to understand what a series is. Example, Taylor series. I will cover a little bit about this. Might give you a little bit of hint about series, but I will not give you too much into what a series is. And then the next thing is I want you to understand about functions, especially one-dimensional functions. So these are all functions with just one independent variable. This is called the independent variable. And one dependent variable. So this is the dependent variable. So I want you to understand functions like this. So these functions are somewhat like functions of time. So as you might have seen this popular example, this is just an audio signal. So this is basically, if you take whatever I'm saying here and then trying to mostly plot it out as the amplitude versus time. So this is going to be your audio signal. If you have any experience with the software Audacity, as soon as you load audio, this is how it's going to look like. As time increases, what is the signal? So I want you to have quite a bit of idea about audio signals, basic one-dimensional functions of time. So throughout this lecture, I'll be using functions in time. What other things? Well, let's jump in and then let's see if you guys need anything more. All right, so what is Fourier series? Fourier series is pretty simple. Any function f of t, I'm just going to call any function f of t, can be expressed as a sum of sine waves. So this is going to be a n sine of 2 pi n times c plus phi n. So that's Fourier series. There you go. It's a series of sine waves. So now when I say any function, there are some terms and conditions which people who are really familiar with this subject might know, which are the Dirichlet's terms and conditions. So what I'm going to say is that almost all reasonable functions can be expressed as a sum of sine waves. So let us take some simple examples of functions that can be represented as sine waves. One is, say, square wave. So this is of period t. This is t by 2. So this is a this kind of circuit is this kind of waveform is pretty common from inverters. So if it is just a single stage inverter, so if you have a DC battery and you want to get AC power, so you get you need to use inverters, and so from DC to AC the conversion might look something like a square wave like this, and this one can be expressed as a sum of a bunch of sine waves. So what do sine waves look like? Just for purpose of hint, sine waves look something like this. So sine waves have a few properties. One is the amplitude. So this is amplitude, so it is A times sine of 2 pi times f times t. So it has a property of frequency. So this frequency is basically, if this length is t, then frequency is 1 by the time period. So how many seconds does in 1 second, how many times do the sine wave go up and down? That's the property of frequency for a sine wave, and then plus a phase by n. So these are the three things that are needed to completely determine a sine wave. So what is this phase phi n? So basically I'm assuming that this is t, so t of, if this is phase phi n, so basically where this should in fact be placed minus phi n, this point wherever it's starting. So it's basically, where are we starting? Is the 0 as t of 0, is it over here? If t of 0 is over here, then phase phi n determines at what phase is this t equals 0 falls in. So basically at t equals 0, where exactly is sine? So phase is just a shift of the sine wave over, so this can take values between 0 to 2 pi. All right, so that is what a sine wave is, and what we are claiming is that any function, say a square function, well, yeah, you can express it. So one of the main things is, today we are going to talk about only about Fourier series. So one of the main considerations for Fourier series is applicable for reasonable functions which are periodic. So for non-periodic functions or aperiodic functions, well, then comes Fourier transform, which is not going to be covered right now, which will be done in a later video. But for now, just Fourier series is applicable to functions which are periodic. So something like the square wave, which keeps on repeating itself, so it is periodically repeating itself. So what's the condition for periodicity? So periodic function basically means don't bother about the new thing that just popped up. I will come back to it later. But periodic function just means that f of t plus t equals f of t. Then this function f of t is periodic with t. So basically this function repeats itself after time of t. That is a periodic function. So any periodic function can be represented as a sum of sine waves. So we will go into a lot more details about what sine waves and everything else later, but first let's just look at an interesting way of looking at it. what I'm going to claim is that any function is just a sum of sine waves. Means if you, the common physics example is basically just any function, take it as white light being made out of a bunch of colors. So R, G, B, and all these other colors start to form. You combine all of them and then you get white light. In a similar manner, any function is actually made out of, any periodic function is actually made out of just a bunch of sine waves put together. So what are these sine waves and everything else? That will be coming in the later sections of this lecture. But this is called the spectrum of a function. Similar to how white light has the color spectrum as it passes through a prism, different wavelengths that are contained in the white light get refracted at different levels, and then you find the rainbow spectrum. Now, similar to that, any function can be separated out. Any function f of t can be separated out into a bunch of different sine waves of different frequencies. Here it is of frequency f naught, 2 times f naught, and 3 times f naught forms this function f of t. So let's go ahead and look into, and this is one of the main reasons why it's called the frequency spectrum or the Fourier spectrum. People use the term spectrum a lot when talking about Fourier series, is because of this. Basically, any function can be expressed as sine waves, and sine waves have the distinct property of having different frequencies. Similar to how different wavelengths of light has different frequencies, sine waves have different frequencies, and hence you can call it a Fourier spectrum when I write it as a series. All right. Now let's talk about history a little bit. Its history is pretty good to remember. So the guy who is responsible for everything is this guy. He is Jean Baptiste Joseph Fourier. I do not know whether I'm pronouncing it right, but he is the guy responsible for it. Well, if you look at his history, he was mostly a politician growing up, and that's why I like looking into history to see how some of the mathematical inventions that changes the world come about. So this guy was a politician during the French Revolution times, around 1760s, and I'm not very sure about the years, but during the French Revolution, he was almost guillotined to death twice. Fortunately, he was an acquaintance of Napoleon Bonaparte, so he kind of rescued Fourier from the guillotine a couple of times, and later he went to Egypt when Napoleon went to conquer Egypt, and because of his contributions to conquering Egypt, he was made a prefect of a town, and that's where he lived for the rest of his life. I mean, apart from occasional traveling, I suppose. But during his time, I would contend that his fame would mostly be from politics, and not necessarily, nobody would generally call him a mathematician, even though right now he has made the biggest contribution in mathematics, arguably the biggest contribution to mathematics, and it kind of shapes everything. Right now, if you're watching this video, Fourier transform has gone in the background trying to compress the video that you have watched so that you can stream it in YouTube or wherever you're watching it. Fourier transform is everywhere. It's in your cell phones. It is Fourier. It's everywhere. It's present from the smallest devices to the biggest devices. It's kind of an indispensable tool nowadays. But back in the time, he was known for mainly his thing, and he initially published his work. His works, not just this, I mean, he also, because he went to Egypt, he wrote about Egyptology and other stuff, and that's where the study of all those other Egyptology as well comes up. But let's come to his main contribution in mathematics. He wrote his paper on Fourier series and submitted it to a journal, and it got rejected. So, well, why was it rejected and who rejected it? Now, who rejected it is actually kind of interesting. It was rejected by Lagrange, and it was accepted by Laplace and two others. And Lagrange was big, and for very good reason. He has made significant contributions to mathematics. If you guys go back and then see, now why did Lagrange reject it? Because Lagrange thought no trigonometric function, because trigonometric functions, sinusoids, are smooth in nature, so no smooth function can exactly replace a pointy function. So that's basically what he said. He said pointy functions like this, which are kind of discontinuous at a point. So at t by 2, if you approach this function from the left, you're going to get the value of 120, and if you approach it from the right, you get the value of minus 120. So this is a discontinuity at the point t by 2. So such kind of function which are pointy, Lagrange said it cannot be approximated by sine waves, and he held this belief long before Fourier ever published his paper, and 50 years after he believed this, when Fourier published his work, it never got accepted, even though Laplace and others agreed to it. And Laplace also made a famous transform which is used in control engineering a lot. Now, the two others are also famous, but I have not read their works, or maybe I have read them and they were not named. So why the reason Lagrange rejected is all there, but Fourier tried publishing it for 15 years. It never got published. And after 15 years, he rewrote the paper and submitted to a different journal, and that's where it got accepted and his book got published. So, well, it took 15 years for it to get published, and later on in this lecture, let's see if we can look at what exactly did Fourier find out. But 15 years is a long time to wait for a paper to get published, if you ask anybody right now. And when it get published, it was actually Dirichlet, a mathematician. I did mention Dirichlet conditions earlier, but that guy in Dirichlet, I don't know whether I'm pronouncing him right either, but Dirichlet was the one who basically came and then laid the foundations, the mathematical basis for it, and then proved that yes, any function which is periodic can be represented as a sum of sine waves. Well, after that, the technique became really famous and it helped solve a lot of problems. But this is something good to think back about patience probably, I don't know. It has some other lessons as well somewhere there, but anyways, moving on. So why do we have to try to express any function as a sum of sinusoids? What's so special about sinusoids? Why sinusoids? Well, when it comes to sinusoids, as to why sinusoids have a few interesting properties, and each one of them is kind of good. So first of all, for anybody who has ever worked on it, sinusoids are pretty easy to define. If you want to completely define a sinusoid, you have, say it's a sinusoidal function of time. So you have A, which is the amplitude, times sine of 2 pi times frequency time plus phase. So you just need three things in order to determine what a sinusoid is. You need the amplitude, you need the phase, frequency, and you need the phase. With these three, a sinusoid is completely defined. But this is not the main reason why sinusoids or why Fourier series became so good, the main reason is this one. Sinusoids are eigenfunctions of linear time invariant systems. This is a little bit complex, so if you do not understand it right now, wait for the rest of the lecture. Towards the end, I will talk to you about this. This is the main reason, actually, why expressing something as sum of sinusoids is really good. And the second main reason is that sinusoids are uncorrelated. So what does uncorrelated mean? Integration over one whole period t of sine of 2 pi f1t times sine of 2 pi f2t dt equals 0 for all f1 not equal to f2. That is, take two sine waves of two different frequencies. They have nothing in common between them. Even though they look alike, there is absolutely nothing. There is no correlation between one and another. So if I say a function is made out of two different sine waves of two different frequencies, then you cannot express, say, sine 2 hertz as, say, a function of sine 1 hertz. No, you cannot do that, because there is no correlation between sine 2 hertz and sine 1 hertz. So that is a very, very, very important property. Now, I said integrate it over one period quite easily over here. So this is what I said, integrate it over one period. So this is a period t. I want you guys to kind of think about why this is periodic. Take Wolfram alpha or MATLAB, and then try to convince yourself that this is periodic. One of the hints that I can give you is this. The period is going to be 1 over f naught, where f naught is kind of the greatest common factor of f1 comma f2. Now if there are fractions, multiply and divide by tens, and then that's what you're going to get. So you need to just say f1 is like 0.1 and say f2 is 2. So find the greatest common factor of 0.1 and 2. Well, you need both of them to be integers first, so you just multiply them by both of them by 10 and then divide by 10. So that's going to be greatest common factor of 1 comma 20 divided by 10. So that's going to be, oops, let's not jump ahead to the chocolate cake. Now GCF of 1 comma 20, this is just going to be 1, so it's going to be 1 by 10. So f naught is 1 by 10, and hence it's going to be 0.1. So what's the time period? Time period equals 10 seconds. So if you see 10 seconds for two frequencies of 0.1 and 2, that's what you're going to get. So you can use Wolfram alpha or MATLAB and then convince yourself that a product of two sine waves is in fact periodic, and as well as when you integrate them over that one period, it's going to be 0 if both the frequencies are different. But on the other hand, if both the frequencies are the same, you're going to get 1 by 2 times, or you're going to get t by 2 if f1 equals f2. You can go ahead and do it and then come back to this same point in the lecture. Now, this is just a side note. I want you guys to recall this from your middle school. This is Euler's formula. So e power j theta cos theta plus j sine theta. J is root of -1. So this is a complex number. So later on I'll be using this a lot. So e power j, here theta is just 2 pi times f times t. So if it is 2 pi times f times t, you get cos 2 pi times f times t plus j sine 2 pi times f times t. All right, let's keep going. So this is just Euler's formula, but the main reason why we use sinusoids, why this became so important is because of these two. One is that it is eigenfunctions to linear time invariant systems, and the second property is that it is uncorrelated. All right, let's go to the chocolate cake. This is going to tell you what uncorrelated means. Let's look at chocolate cake. There are two recipes here. One is 3 eggs, cocoa powder 3 tablespoons, milk 1 cup, sugar 3 cups, flour 4 cups, butter 2 sticks of butter. So if you are wondering where I got such a crazy recipe, it is from my students in fall 2019 class, and this is the recipe that they gave. Or maybe it results in a good chocolate cake. I wouldn't try it out. If you are daring enough, please do. I think it might be edible if you bake it all together. Well, this is a recipe, and then you got the second recipe, which is, say, milk candy 2 cups, mom's Dow cocoa mix 1 cup, butter egg mix from previous cake 3 cups, sugar butter mix from breakfast 1 cup. So if I give you the second recipe, I don't think you can make the same chocolate cake that I did. But on the other hand, if I give you the first recipe, you guys can make, at least you guys can recreate the same chocolate cake that I can make. Why is it? For one thing, these functions or these things are kind of harder to define. What is mom's Dow cocoa mix? It might be different for different moms. So you don't know that. What the hell is a milk candy? It's what ratio of milk and what ratio of sugar are going to be there. So what is this? So there is a lot of problems with the second recipe, whereas the first recipe is pretty simple. There are 3 eggs, 3 tablespoons of cocoa butter, milk 1 cup, sugar 3 cups. All these are distinct ingredients. So expressing a function as a sum of, let me get it out. So if I have a function, so chocolate cake, take it off, think of it as a function, f of t. F of t can be represented as, or can be made by mixing all these functions. So this is say a square wave, and probably this is say a triangular wave, and this is probably a DC function, so on and so forth. So you can use, probably you can construct your function using the sum of such kinds of functions. On the other hand, this is like sine waves. So this is sine of frequency f1, sinusoid of frequency f2, sine of frequency f3, so much quantity. So you're just mixing a bunch of sine waves. So what does that mean? So what I'm saying here is that just like eggs has nothing to do with cocoa powder, both are entirely different ingredients, two sine waves of two different frequencies are entirely different. There is absolutely no correlation between this one and this one. So that is, if there is frequency f1 and there is frequency f2 of a sine wave, both of them are entirely different ingredients. So when you are saying it as eggs as 3 and cocoa powder as 3 tablespoons is equivalent to saying that the function is made out of sine of frequency f1 and sine of frequency f2. On the other hand, square wave and triangular wave has some correlation between them. So if you integrate a square wave multiplied by a triangular wave, you're going to have some correlation between them. And hence, the triangular wave has something of the square wave. The square wave, on the other hand, has some commonality with the triangular wave. So when I'm saying milk candy, probably this has sugar. This also has sugar. So now, how much is the total sugar that I need to add? Now you cannot know that from just a recipe like this. In the same way, if I just tell you square wave and triangular wave was present in this, you cannot easily say like, okay, how much of square wave? You can probably translate, you can reduce the amount of square wave and increase the amount of triangular wave, and you're still going to be good and still make the same function f of t. And so this is not really a good representation. But sine waves, on the other hand, is like saying distinct ingredients. One has no relationship to the other, like eggs, cocoa powder, milk, sugar, none of them have any relationship to the previous one. So basically, Fourier series is the recipe to make f of t. That's it. So that is Fourier series in a nutshell. And why do we use sine waves? Because they are distinct ingredients. It's like saying, and anybody in the world can easily understand what's going on. That's why let's go to the next definition of sine waves. Sine waves, sinusoids, are the Fourier atoms. So, or the Fourier basis. It's called the basis functions or the Fourier atoms. There are lots of different definitions for this. So why Fourier atoms? Well, any material could be said as made out of a bunch of different atoms. So if I take plastic, I can say so many carbon atoms, so many hydrogen atoms, so many hydrogen atoms or carbon atoms, maybe some more other atoms, some ammonia atoms and other stuff. So nitrogen atoms and other stuff. But well, similar to stating atoms make up a material, any function f of t could be said as to be made out of sine waves. That's the exact same argument from the chocolate cake, which I just said, just that atoms is a term that is professionally used in the signal processing community. So when you talk about Fourier atoms, everybody raises their eyebrows in understanding. Well, that's it about Fourier atoms. Now, let's look at these Fourier atoms. So the Fourier atoms are A times sine of 2 pi n times f times t plus phi. What's the frequency? This is the frequency of the sine wave, and this is the phase, and this is the. So this corresponds to the Fourier atom. Now, what we want to do is to put them all together as a recipe book. All right, now I'm going to talk about the Fourier recipe book. So let's look at it. So what is the Fourier transform? Is A times sine of 2 pi times n times f times t plus phi. So there is amplitude, there is frequency, there is phase. So any function f of t is just made out of a bunch of these n equals, say, 0 to infinity a n sine of 2 pi times n times f times t plus phi n. This is what you're going to get. So this is your frequency axis f. Now, this is basically your Fourier series. So basically, you have the function f of t, which is just a bunch of sine waves put together. So what are the sine waves present? You got all these frequencies n times f. So I'm just going to put them all together. So what are the frequencies present? Say maybe I have, say, 0, f, 2f, 3f, 4f. So these are all the frequencies that are present, and I'm just going to call it amplitude and phase. So 0, f, 2f, 3f, 4f, 5f, so on and so forth. And what is the amplitude? So this is going to have the amplitude of A0, A1, maybe 2f is not there, maybe A2, A3, A4, A5, so on and so forth. So this, this is A2, 3, 4, 5, 6. So this is your recipe book. Both of them combined together. So you also have phi n. I can write it as, so this is going to be between plus pi and minus pi. So the values are going to be somewhere in between in all the cases. And if you plotted this function in time domain, this is how it's going to look like. So this is f of t versus t. So if you look at it in the time domain, maybe this is the function. And maybe it repeats itself after this. So it just goes again. So this is your function. So it is periodic with period t. So this will be your periodic function. So let's look at this periodic function. So this periodic function is equivalent to this. So how do you make this function? You add a sine wave of frequency 0 with amplitude A0 and phase, say, pi by 2. So that is going to be a cos wave. So sine of theta plus pi by 2 is cos theta. So you're going to get, say, pi by 2. So it's going to be just A0 because cos of 0 hertz is just a DC function, so it's going to be A0. But anyways, that's for later. Just to make this function f of t, you need to add up all these sine waves. So the first sine wave is of frequency f, second is of frequency 2f, 3f, 4f, 5f, so on and so forth. So you add all these sine waves of these frequencies with these amplitudes and these phase, and you get your Fourier transform. Now, you might have heard the term frequency response and everything else when you are buying a microphone, or if you are buying a headphone and other stuff. So this is basically what they are talking about those responses, but we will come to that in the later parts of the course. The main thing that I want you guys to take away from this is that any function f of t can be expressed as in this format, as a plot of amplitude versus frequency and a plot of phase versus frequency. So these two combined gives you the recipe for forming f of t, and this is called frequency spectrum, and in fact this is particularly called the magnitude spectrum, and this is called the phase spectrum. So these are the two terms for these two plots. So basically a plot of the amplitude of the sine waves that are needed to form f of t, and that is going to give you the magnitude spectrum, and the phase spectrum is the phase of the sine waves of different frequencies that are needed to form the f of t. So that's going to be your phase spectrum. Now, that being said, let's look at sine waves in general. As I have written down a couple of times already, you got the first method of representation, which is a times sine of 2 pi times f times t plus 5. So basically this is the frequency. So what if f equals 1? So f equals 1 means it completes one cycle in 1 second. So 0, this is 1 second, and this is time. So this is f of t equals sine of 2 pi t. If it is amplitude 1, if it is a times sine 2 pi t, the amplitude will be a. So that is that about that, and then the phase is going to be basically just a shift of this. So it's probably like, if it is something like this, then this is going to be the phase phi. All right, so if this is your 0, so this is going to be the phase phi, and this is going to be the amplitude, and this is a pretty simple format. All right, so this is one representation. Now, you can write this exact thing using the trigonometric identity as this. Basically, what I'm using here is sine a plus b equals sine a cos b plus cos a sine b. So what happens is this a is nothing but this term, this b is nothing but this term. You guys can go ahead and verify this. So this is going to be b, and this is going to be a, and this is b, and then use this formula sine of a plus b, and then you should be able to get this format for this. So this is another representation of this. So if you guys do not remember the trigonometric identities, I will give you a very easy way of remembering them. E power j theta is nothing but cos theta plus j sine theta. So now e power ja times e power jb equals e power j times a plus b, because just multiplication of product. Whereas now you can expand this as cos a plus j sine a, and then this one as cos b plus j sine b equals cos of a plus b plus j sine of a plus b, and then equate the real and imaginary parts, and you should be able to get the identities for sine a plus b and cos a plus b after multiplying these two. All right, so that is just a small hint as to how you can proceed with understanding how the trigonometric identities work. Actually, you can use Euler's formula to derive almost all the trigonometric identities out there. Now, with all that being said, now the third way in which you can represent sine waves, or a sine 2 pi ft plus phi, is using two of these guys. So this uses the fact that cos of 2 pi ft equals e power j 2 pi ft plus e power minus j 2 pi ft by 2, and sine of 2 pi times f times t equals e power j 2 pi ft minus e power minus j 2 pi ft divided by 2j. You use this, you substitute it into representation 2, and then you can get representation 3. All right. So these are the three ways of generally representing a sine waves, and based upon that you can have different styles of recipe books. Either you can get this is called the complex form of the Fourier series if you express it in terms of e power j 2 pi ft, and this is called the just a sine and cos expansion of a Fourier series. So you will see Fourier series in both the formats. Now the next slide is just going to show you the equivalence between these two guys. So it is kind of fun to see as phi is increasing. This notation, sine of 2 pi 10t plus phi, is equivalent to an cos 2 pi 10t plus bn sine 2 pi times 10 times t. So this code was written in MATLAB. You can get it from me later. Now, I told you that any function f of t can be expressed as a sum of sine waves. So how many sine waves are needed? So for this question, I'm going to answer it in two formats. One is, if it is pointy function, then countably infinite number of sine waves. If it is a smooth function, no or a continuous function or a smooth function with no discontinuity, that is, it is infinitely differentiable everywhere, then finite number of sinusoids. So what is countably infinite? Well, the natural numbers are countably infinite because you can go 1, 2, 3, 4, 5, so on and so forth. So you can actually count them. And then how many natural numbers are there? There is infinite. This is in contrast to uncountable infinity, in which is like real numbers. How many real numbers are there? Can you start counting real numbers? No, you cannot count real numbers because there is 0.0000. Well, you can never count real numbers. So that is an uncountably infinite. So compared to that, there is just countable infinite sine waves. So you can actually count the sine waves, like, okay, sine 1 hertz is there, 2 hertz is there, which results you can do partial sum. If it is countable infinite, then partial sum is allowed, and then it's easier to kind of make an approximation with a reasonable number of sine waves. It will be reasonably close. Let's look a little bit more deeper into this. I want you to verify for yourself that sine of 2 pi times f naught times t plus sine of 2 pi times n times 2 times f naught times t plus sine of 2 pi times 3 times f naught times t has the same frequency f naught. It's all periodic. Basically what I'm trying to say is that the time period Tp equals 1 by f naught. That is, you add as many sine waves as you want. Basically you can add n sine of n equals, say, 0 to capital N number of sine waves, 2 pi times n times f naught times t. This is going to be periodic with period t equals 1 by f naught. Remember, this is in accordance with how I told you to figure out the time period earlier. So the basically GCF of f naught plus 2 times f comma 2 times f naught comma 3 times f naught is nothing but f naught. Definitely f naught. So that means if you are adding a bunch of sine waves, each of them differing in frequency by an integer number. So the first sine wave is of frequency f naught, the second sine wave is of frequency 2 times f naught, third sine wave is 3 times f naught, so on and so forth. It's going to have, the combined one is going to have a frequency of just f naught. This gives a hint as to what sine waves you would need to represent any function. So this is, say, f of t versus t. So this is, say, periodic with period t. So it has a, this is called the fundamental frequency. One by t. Of course, it is periodic with period 2t as well, but the fundamental frequency is corresponding to the first repetition. So how long does it take for the wave to repeat itself? The smallest amount of time with which the wave repeats itself, that's called the time period, and the inverse of that is going to be the fundamental frequency. And so for a function which is periodic with this fundamental frequency, if I'm expressing this function as a sum of sine waves, the sine waves should have frequency f naught, 2 times f naught, 3 times f naught, 4 times f naught, so on and so on, or 0 f naught. So basically n times f naught for all n equals 0, 1, 2 or integers. So these are the frequencies that would be needed to represent any periodic function with period t, which is pretty cool. So these are just a distinct set of frequencies. So you can count it. There is 1 of 0 frequency, there is 1 of f naught frequency, there is 1 of 2 times f naught frequency, 3 times f naught. So that is countably infinite, possibly, but you can still count it. So it's a countable set of sine waves that are needed. The interesting thing is, if you just add up a bunch, it's going to come pretty close. So you, as engineers, the one thing that you would need to do is just know how many sine waves you need to add. That's pretty simple. That's about it. And then the next thing, so now we know what are the sine waves that we'll be needing. So basically, what are the frequencies of sine waves that we'll be needing? So now comes the first part. If a function f of t is periodic with period t. So its fundamental frequency is f naught 1 by t. Of course, this repeats itself everywhere. So such a kind of function will have the Fourier recipe book basically like this. You will have 0, f naught, 3 times f naught. These are the sine waves that will be present. So these are the only frequencies you will need. And generally, notational wise, we just use capital F of 2 pi j times f, and this is magnitude, and we also need phase, angle of f of 2 pi times f. And there you go. That's going to be your Fourier recipe book. So these are the sine waves that will be needed to put this, and of course the quantity is going to vary. Some might, based upon the amount of the magnitude of the different sine waves, you are going to have different functions. Well, and that completes the basic of it. Now we need to understand what exactly are these. So what's the quantity? You now know the frequencies, but you need to know the quantity, and this will be taught in next class. All right, see you later.